Watch this. I tell the agent my name is Priya and my database is Postgres 16. It answers perfectly. Now I close the session and open a new one. Same agent. One question. What database do I use? I do not have that information. Nothing broke. The model never remembered anything, not even during that first conversation. Then I add a memory layer, ask the exact same question, and the answer comes back. Postgres 16. Here is what actually changed underneath. Every memory system you will build is these two tiers. On top is the context window. That is everything the model can see right now, and it is rebuilt from scratch on every single request. Underneath is storage, a database that outlives the conversation, and that the model cannot see at all. Not one byte of it, until your code goes and fetches something and writes it into the tier above. That gap between the two tiers is the entire subject of this lesson. Here is the part that surprises everyone. The model is a pure function. Text goes in, text comes out, and it keeps nothing in between. When a chatbot remembers your name from 3 turns ago, that is not the model remembering. That is your code sending the whole conversation again every single turn. Turn 1 sends 2 messages. Turn 2 sends 4. Turn 3 sends 6. The history is not stored on the model's side. It is reread from the beginning every time you call. Here is short-term memory with nothing hidden. It is a plain Python list. Every turn you append what the user said and what the agent said, and you send the whole list again. Turn 1 sends 2 messages. Turn 3 sends 6. There is no server holding your conversation. That list, in your process, is the entire memory. So short-term memory is really a budget, measured in tokens. Claude Opus 5 gives you 1 million of them. That sounds like plenty. It is not, because you are not just paying for chat. A working agent's window holds the system prompt, every tool definition, retrieved documents, and every tool result it has read. In a long run, the conversation is often the smallest thing in there. And the budget is a hard ceiling. When it fills, something has to go. So just use the million tokens. Here is the part that should not work, and does not. Researchers buried one fact at different depths inside a long context and measured whether the model found it. Accuracy is high at the start, high at the end, and sags in the middle. Over 30% worse when the fact sits mid-context. That is the lost in the middle result, and it held across 6 model families. A later study tested 18 frontier models. Everyone degraded as the input grew. The budget fills. You get 2 honest choices. Truncation drops the oldest turns. It is cheap, and whatever falls off the edge is gone silently. Compaction summarizes those old turns into one block and keeps the summary instead. You hold the gist of far more history, but summarizing is lossy, and any detail that did not make the summary is gone for good. Claude's API ships both context editing, clears old tool results. Compaction rewrites them. Neither one is memory. Both are damage control. Long-term memory starts with the question. People skip. What is actually worth keeping? Not the transcript. You extract the durable fact. From I am on Postgres 16 and please stop suggesting Mongo, you store one record. User 42. Preferred database. Postgres 16. That is 20 tokens instead of 2000, and it is still true next month. Claude's own memory tool works exactly this way. It writes small files that outlive the session, store facts, not conversations. Next session you ask, what should I use for storage? You never said the word Postgres, so exact text matching finds nothing. Instead, the query is turned into an embedding, a list of numbers, often a few hundred to 1500 of them, that places the meaning in space. Every stored memory has one too. The store measures the angle between them. That is cosine similarity. Your query scores 0.91 against the Postgres record and 0.06 against an unrelated one. The closest few get pasted into the window. Here is the similarity itself, with nothing hidden. Multiply the two lists, position by position, add it up, then divide by their lengths, so only the direction counts. Real embeddings have around 1500 numbers. 3 is enough to see it work. The storage question scores 0.91 against the Postgres fact and 0.06 against the city. That gap is the entire retrieval decision. Now the distinction that changes how you design the store. Episodic memory is what happened, a dated event. On March 3rd, the deploy failed on migration 7. Semantic memory is what is true, a fact with no timestamp. This user's database is Postgres 16. Procedural memory is how to act, a rule. Always run migrations on staging first, and they belong in different places. Episodic records go stale and should expire. Semantic facts get overwritten when they change. Procedural rules belong in the system prompt, not in a lookup. Now, put it together. Session 1 runs. At the end, 3 facts are extracted and written down. The session ends, and the entire context window is destroyed. All of it. Session 2 opens with an empty window. Before the first reply, your code queries the store with the new message, takes the closest matches, and writes them into the window as text. The model reads like anything else. The model still remembers nothing. Your rig remembers and hands it the answer just in time. The 2 tiers, one more time. On top, the context window, rebuilt every request, capped by a token budget, and degrading in the middle when you stuff it. Underneath, storage, facts you chose to keep, found by meaning, and injected on purpose. The model has no memory. Memory is the system you build around it. Once you see that, agent memory stops being magic and becomes plumbing you control.